Welcome to lesson 49. So this should be a throwback to back when we were doing single factor ANOVA. Our first step was to say, hey, is at least one of the means different? And then our follow-up was to say, well, which ones? In this case, for what we're doing here with our testing multiple explanatory variables, we ask, is at least one explanatory variable useful? Our follow-up should be, okay, well, if at least one is useful, which ones? So we're going to talk about our hypotheses, the test statistics we use, p-values, and interpreting. So interpreting these relationships, so this is the model we fit for our Mario Kart example. We found there was very, very strong evidence that at least one of the explanatory variables, so the starting price, the number of Wii wheels included, or the condition used or new, was useful in predicting the selling price of the eBay auction game Mario Kart. So specifically, we came up with this example here. So we should also say that Y hat is the predicted selling price. That's important. As well as X1 stands for the starting price of the bid. So this is in US dollars. X2 is the number of wheels, so 0, 1, 2, 3, or 4. And condition, new or used. So it was given a 0 if it was new and a 1 if it's used. R tends to, by default, put these categorical variables in alphanumerically. So because new comes in the alphabet first before used, new was 0 and then used was 1. So absolutely, once we perform that overall F test, then we can perform individual T tests to find out which explanatory variables are useful in explaining the selling price of the game. So if a variable is not significant when the others are included in the model, it's possible that we should exclude that particular variable. So if we went ahead and we ran t-tests for all of the explanatory variables and found, hey, this one is the least significant out of all of them, it has a very large p-value, try fitting the model again, excluding this variable, and see how it fits. Only ever remove one variable at a time. This is so important. Only ever remove one at a time. Never remove more than one at a time. I cannot stress how important it is. Because a lot of times if you remove one, it really changes the impact that the other variables have on the response. So looking here, individual t-tests for the slope coefficients. This is when it's really, really important to keep track of what order you put the variables into your linear model. So if you were in R and you said linear model and you have response and you put, okay, well, by my first explanatory variable, by my second, by my third. You want to keep track of what order you put these variables into your model, because that tells you if it's beta 1 or beta 2 or beta 3. And you'll be able to tell from the output as well. And we'll talk about that. So our conditions, they're going to look much the same. So we need to know that we have a representative sample. Easiest way is to have a random sample. We need, when we have our residuals versus fitted plots, to know that, hey, we have linearity, we have independence, we have normality, and we have constant variance. And you need to have a big enough sample that the number of explanatory variables plus 1, that needs to be smaller than your total sample size. You really need to have a big enough sample that you don't have, a sample of 10 and 9 or more explanatory variables. That won't be useful. So our hypotheses here, I'm going to plug these in here. So these individual beta j is equal to 0, so there's no relationship between whatever particular explanatory variable and y. This is important though, when you include the other explanatory variables in your model. Versus your alternative saying there is a relationship, so it is useful to include this particular explanatory variable even when you have the other explanatory variables in the model. It's always going to be a two-sided test, just like it was last week. Our test statistic is going to be a t statistic. It'll be our estimated bj, so our estimate for beta j. minus 0, because that would be our null claimed value, over standard error. We don't expect you to calculate the standard error by hand. These are things that you can take from our output. And then once you get this t-statistic, you're going to use a t-distribution that has degrees of freedom equal to your sample size minus the number of explanatory variables plus 1. So you can think of it as n minus the number of explanatory variables minus your overall mean, kind of. That's what it's getting at. Absolutely, the standard error is super complicated to calculate by hand. This is not something we expect you to do. This will not be something we expect you to do at all. It's gross. In your masters, you do it maybe once or twice. Then they never make you do it again because we have software. It's a little old school to do it the other way. So looking here at individual t-tests, so we're going to do, first off, we're going to look at the Mario Kart example. Then we'll look at the GPA example. So for the Mario Kart example, if we use a significance level of 0.05, we want to know which variables are statistically significant while including the others. So I know at least one of starting price, number of wheels included, and whether or not it's used is useful. I want to know which ones are useful. So looking here, so I'm going to adjust the mic here. Nope, that didn't help. I want to know which ones are useful. So starting price, this means I'm going to look at this row. So this is so note, I'm testing for beta 1, beta 2, beta 3. And that's just because of the order I put them in. Absolutely, you can change that order around depending on your equation. If you do LM and you do used plus wheels plus start price, it's going to change the order they pop up in. Not a big deal. So starting price, looking here. Here is my t-statistic. So I have a t-statistic of 4.824 and a p-value of 3.7 times 10 to the negative 6. That's tiny. So I'm going to say divided by not divided by, but less than 0.0001. That's true. That's plenty small. So if I have a t-statistic of 4.824 and a p-value that's really tiny, that would tell me that starting price is very useful to include, even when you already have wheels and condition, either new or used, in the model. So I would say it's significant here. And then I'm going to make my way through here. Absolutely, this is a great place to pause. Go ahead, test this yourself, write it out, then check your answers. But obviously, you're free to do as you will. So t, usually the bigger your t-statistic, the smaller your p-value will get. 3.406. So less than, I would definitely argue it's less than 1 in 1,000. 2 times e to the negative 16, that's really tiny. Imagine at least, so point and then at least 15 zeros. It's very, very, very tiny. So if that p-value is tiny, that means the number of wheels included is really, really useful in figuring out the selling price. If I look at used, same deal here. I'm going to have a t-statistic that's pretty big here, or magnitude is, that p-value is pretty tiny, so it's less than 0.001. I'm also going to say this is significant. So in this scenario, for the Mario Kart example, we found that all 3 of these happen to be significant. So the overall F-test told us at least one was. The individual t-test told us which ones were. So here, we performed something similar with the GPA example, but we might have some contradictory findings here. Especially look here. That estimate's itty bitty, but we'll look. So high school GPA, we're going to look at, I had a T statistic. Remember, the GPA example was based on 10 data values. So we only had 10 observations. It was very small. So I had a T statistic of 1.909 and a p-value of equal to 0.0979. That's pretty big. At the 0.05 significance level, I would argue that this is not as significant. So high school GPA is not significant. If you want to get weirder, we're going to look at the next. So looking at SAT, because remember last week we felt, yes, high school GPA was useful in finding college GPA. Well, let's look at SAT as well now. So I have a T statistic. My T statistic's even closer to 0 here. 0.570. And I had a huge p-value there, 0.5868. A huge p-value is really weak evidence. So the SAT score is not significant. So one thing I want to emphasize is here, we wouldn't rush to say that neither of them are useful. What we would do is we'd say, okay, which one's least useful? Oh, well, this one. We would remove SAT and fit again. And then find out, okay, well, when I remove SAT from here, is high school GPA useful in predicting college GPA? You'll find that it will be. And in part, what's happening here, the reason that neither of these appear significant is because they're related to one another. R or any stats, whatever, it's not sure who to give credit to, who's explaining what. Because high school GPA and SAT scores are related to one another, it doesn't know who to give credit for explaining variation in the college GPA. So absolutely, when things are related to one another, there are things that we have in place to do. Absolutely, you don't want to be putting related explanatory variables in there together like that. It gets really gross really fast. So now we're going to look at basic model selection. Specifically, we're going to look at, I think, backwards model selection. So my first model here, so this is my first model. You can see here, it includes high school GPA and SAT. And when you look here, your F statistic, it's 7.508 on 2 and 7 degrees of freedom. Your p-value is pretty strong. It's saying, hey, at least one of them's useful. But when you look at them individually, you don't see that at least one of them's useful. What's most useful to try next is to get rid of the one that's the least useful. So both of my p-values are over 0.05. This one's the highest. I would honestly try removing SAT. But here, we went ahead and we fit 2 more models. So the second model here, it only has high school GPA in it. So my F statistic is 16.05, so that's gone up on 1 and 8 degrees of freedom. My p-value is tinier. So it's saying, yes, definitely at least one of these explanatory variables are useful. Looking here, we only included 1. So when you look here, I have a T statistic of 0.4006 on 8 degrees of freedom with a p-value that's 0.00392. That's tiny. So saying absolutely high school GPA is useful to use. However, if you look here at scenario 3 or model 3, this one is fit with only SAT. So I'm predicting college GPA, their first year college GPA by SAT. I get a T statistic of 2.9 or so, which is smaller than this 4.006. And I get a p-value here, which is larger than this one here. So I would go with model 2. Absolutely. Either way, you wouldn't want to go with model 1 because model 1, even though it says at least one of them is useful, you don't find that either individual one is useful. Models 2 and 3 looks at individually high school GPA and individually SAT. But if you look here, individually high school GPA is the most useful. So I would go with predicting first year college GPA with using high school GPA. So there's lesson 50. We'll see you in a minute.